All right, hello. We're going to cover section 6.6, in which we talk about solving logarithmic and exponential equations. Now, going back to when we first learned about equations, what we're wanting to do is find, values of the variable in question which satisfies the equation that is presented to us. We're going to start off by looking at logarithmic equations, in which we typically have at least one logarithm in the equation, and the argument of the logarithm would contain the variable. Now, remember, and I'm sure that you guys have already talked about this previously, when we talk about logarithm base A of x, and we're saying that that is going to be what y is, that's the same thing as saying that whatever that base A is, some number, raised to the y power is equal to x. When we take the log of a number, we're looking for an exponent. We're saying that x raised to what power is equal to a, or a raised to what power is equal to x, I should say. So this is just kind of a reminder of what a logarithm is, what log base a, whatever a is. Typically we use the natural logarithm, which is base e, and the base 10, but we can talk about any base, logarithm of any base. So when you see a log base a, that's just a generic logarithm of any base a. Now, if we say that log base a of some number m is equal to the log base a of some other number n, the only way that this could be true is if the two numbers m and n are exactly the same as each other. Okay? And we're going to use that fact to help us solve logarithmic equations. Now, of course, when we say this statement right here, where we're going to assume that m and n are positive numbers, because after all, you can't really take the logarithm of a negative number. You can't have 0 or a negative number as the argument of a logarithm. And also the base has to be positive. Doesn't make sense to have the base of a logarithm to be 0 or negative. And it doesn't make sense for 1 to be the logarithm of, it doesn't make sense for 1 to be the base of a logarithm, so we'll assume that a is not equal to 1. A could be a positive fraction, like 2/3 or 3/5 or whatever, and a could be greater than 1. But a is not going to be 0 or negative, and a is not going to be 1. Okay. So, when we go about solving logarithmic equations, we're going to make use of this fact right here, that if you take log to the same base of two different numbers, well, the only way that this equation could be true is if those two different numbers are really the same. Okay. So we're going to start right out of the chute and say, let's just suppose that we've got this equation right here, got log base 3 of 4, and that's equal to 2 times the log base 3 of some number x. And the question is, what is x? What is x in order for us to solve this equation, in order for this equation to be a true statement? So we're going to look at a sequence of steps. So, what is the first step you think that we can make in order to solve this equation? Anybody? Any ideas? Yeah, exactly. We're going to make use of the fact that when you take log of some number raised to a power, then that's going to be the same as that power coming down as a multiplier in front of the logarithm. Okay, we're going to make use of that property of logarithms. All right, I'm going just to erase this ink here. Okay, so we will, go ahead and use that that property of logarithms. All right, what's the next step? Okay, we're going to make use of the fact that if you have log of a number is equal to log of some other number, and those logarithms are equal and you have the same base, what does that say about these numbers here, this one and this one? That they would have to be the same in order for that equation to be true. Okay, I agree. So that means that 4 must be equal to x squared. So what does that make x? X could be or negative 2. 2 or negative 2, right? Because if I say that x squared is equal to 4, that means that x squared minus 4 is equal to 0, right? That means that x minus 2 times x plus 2 is equal to 0. That means that either x is equal to 2 or negative 2. Okay? So you have two possible solutions, maybe. I say possible, because what do you do when you come up with these possible solutions, right? But what do? You go back and check your answers, right? You go plug in the numbers. Now, if you were to plug in 2 for x here in the original equation, I'm going to erase all this ink here. Now, if you were to take, plug in 2 right here for x, and then look at the left-hand side. Now, 4 is 2 squared, so you could bring down the 2, and then you would have the left equal to the right, right? But what if x were equal to negative 2? Does it make sense to take the logarithm of a negative number? No, it doesn't. So that means that we're going to probably eliminate the negative 2 from consideration, right? So that goes along with this idea that you learned a long time ago when you first started studying algebra and solving equations, is that you come up with these numbers that are possible answers, but before they really are solutions, you have to check them, right? By plugging them back in. Any questions so far about solving these equations? Okay. So the solution, the one and only solution is going to be 2. All right, here's our next problem here. We have this equation involving log base 2. So we have log base 2 of x plus 2 plus log base 2 of 1 minus x is equal to 1. So what does x have to be in order to solve this equation? So think about all the properties of logarithms that you can use. Now, is it possible to combine these logarithms? What do you get when you are adding 2 logarithms of the same base? Can you make use of the fact that log of the product of 2 numbers is the same as the sum of the logarithms of those 2 numbers? And yeah, exactly. We're going to use that property of logarithms that says that log of x plus 2 plus the log of 1 minus x is going to be the same as the log of x plus 2 times 1 minus x. Okay? Does that make sense so far? Okay. And then you probably know what to do. If I say log of this, whatever it is equal to some number on the right, what do I need to do to solve for this argument? Well, you typically look at the base of the logarithm and then exponentiate both sides of the equation with that same base. So we're going to use base 2 of exponentiation both sides, right? Because when you exponentiate with base 2 of the log base 2, those will cancel each other right? Because exponentiation base 2 and log base 2 are inverse operations of each other. All right, so I'm going to erase this ink and advance my slide here. All right, so exponentiate both sides with base 2. And where did the 2 come from? The 2 is because we had 2 raised to the 1 power, and then we swapped the sides. And now we have this polynomial equation, so multiply out the right-hand side, FOIL it out, right? And then, solve it like you would any other polynomial equation. Maybe combine those x or those constants of 2. They happen to cancel each other out, right? So, and then you have x squared plus x is equal to 0. And then you could factor that polynomial as x times x plus 1 equals 0. So that means by the 0 factor property that either x equals 0 or x equals -1. And, are both of those viable solutions? So we could plug in the 0 for x. What happens if you plug in 0 for x there and there? Then you'd have log base 2 of 2, which is 1, by the way, and log base 2 of 1. What's log of 1? Log base anything of 1 is always going to be 0, right? So that means that this would be 0. And log base 2 of 2 is really equal to 1. So 0 really is a solution, right? But what happens if you were to plug in -1 for x? Let me pull out my little eraser here. Now, if you plug in -1 for x there and there, you'd have log base 2 of 1, which is 0, and log base 2 of, we have 1 minus -1, which is 2, so log base 2 of 2, which is 1. And that will also be a true statement. So -1 is also a solution. So folks, make sure that you always check these potential solutions to verify that they really are solutions. In this case, both of these really are solutions, okay? Because of the fact that both of these numbers, 0 and -1, are in the domains of both of those logarithmic functions. Okay. Any questions so far about solving log equations? So far, pretty straightforward? Okay. Just got to remember all of those log properties that you learned last time. Those are going to be useful in helping you solve these equations. And more importantly, who's going on to calculus? By the way, anybody going on to calculus? Taking calculus 1 soon, in the next year or two? Well, folks, logarithms are pretty darn handy in manipulating equations and expressions and stuff. So it behooves you to know your logarithms quite well. Okay, so now remember that the exponential function and the logarithmic functions are inverses of each other. And they pretty much have the same properties. Including this property that says that if you have some exponential function with base a, and you have a raised to the u power, and that's equal to a raised to the v power. A is some number, right? A is some positive number. What does that mean? That means that u and v have to be the same. So we're going to use this fact in order for us to solve the exponential equation. Now, again, we're assuming that the base is positive and not equal to 1. Because it doesn't make sense to have an exponential function with base 1, because 1 raised to any power is equal to 1. All right, so here's our first equation to solve for x. So 3 raised to some unknown power of x is equal to 7. what does that power of x have to be in order for this equation to be a true statement? So how do we solve it? Well, one way that you could do this is take, log base 3 of both sides. Why log base 3? Because log base 3 is the inverse of the exponential function of base 3, right? Or you could take log base 10 or natural logarithm or log of any other base that you want. But hey, keep in mind, you're going to have to get some sort of approximate answer in order for your calculator to evaluate this. Your approximate answer needs to be in a base that your calculator can use. And all calculators, besides the normal little 10 key things, can do natural logarithm or base 10. So I'll show you one possible solution is that you could take natural logarithm of both sides. You could just as well take log base 10 of both sides. But ln, remember that's the natural log. That's log base e. So take natural log of both sides. And then what's the next step? Well, you have this x as the exponent. How can we get this exponent down from there? Well, we're going to use that same property that we used a few problems ago that says that the log of the power is the power times the log, right? So that x is going to come down as a multiplier, right? Natural log of 3 to the x is the same thing as x times natural log of 3. And natural log of 3 is a factor, right? So you have x times natural log of 3. So how do we solve for x? We divide both sides by natural log 3. Treat natural log 3 as any other number. So divide both sides of the equation by natural log 3. By the way, does Lacey teach like this? Or does she use the board? She uses the board, okay. So this is a little bit different for you guys, huh? I know.
Yeah, you just type it in and just put it on.
These are actually the publisher slides. If you look on the bottom, there's the trademark down here. So these actually came with the text materials. So a lot of instructors have been teaching the same way for many years and don't like using it or just are not aware of using it. But because of the fact that I teach a lot of online classes, I use the PowerPoint slides. Big time saver for me. And then I create some of my own content as well, sometimes for some slideshows and for some courses. I've never had to really create slide decks from my own self, but one of these years I think that I'll take an entire summer off and just, for some of the courses where there's very slim pickings for PowerPoint slide decks, I'll create my own stuff from scratch. But this is okay. Now this is something that we could do. Now I'm going to give you a minute. Go ahead and pull out your graphing calculators and evaluate this. Natural log of 7 divided by natural log of 3 and see what you get. I want to make sure that you actually know how to evaluate these logarithmic expressions. So make sure that you use parentheses. Hey, I'm going to pull out my graphing calculator too. Here's my graphing calculator. In parentheses, I'm going to do natural log of 7. And you don't have to use parentheses, but some people feel more comfortable with like a little comfort blanket, kind of natural log of 3. So you could do it this way. So there's the input. But like I say, you don't really have to use parentheses. You could just do that. But make sure that you put a parentheses after the argument for each of the logarithms. Okay. So did you get this answer? Okay. Any questions about using the graphing calculator to evaluate logarithms? No? Yeah. Okay. Okay. How do you all do your homework? Is it pencil and paper homework or do you online homework? My Math Lab? Okay. So you're only too well aware about making sure that you read the instructions before you input your answer. So, because it's picky about how many decimal places that it'll accept, right? So it'll tell you to round your answer to 3 decimal places. So I will tell you that when you have to evaluate an expression like this is to keep everything together in one entire calculation, because if you break this up into 2 steps and you round at each step, then you might have too much round off error, in which case your answer won't agree with the computer's answer. Okay, so stick the whole thing into your calculator. Okay. All right, moving along here. Here's our next problem. 5 times 2 to the x power is equal to 3. What is x? Now, this time I'm just going to put my pencil down and give you a minute and see if you can solve this. All right, so I'll give you about 2 minutes. See if you can solve for x. And I'm going to... Okay, so we took a quick pause to solve the problem. Let's see what we came up with. So our next step would be to divide both sides by 5 so we can get that exponential by itself on one side of the equation. So we have 2 to the x raised, we have 2 raised to the x power is equal to some number, that number being 3/5. It's just a number. So what does x have to be in order for this equation to be true? So you could take a logarithm of both sides in order to solve for x. Again, it doesn't really matter what base the logarithm is, but if I were you, I'd use natural logarithm. So take natural log of both sides. Like I said, you could use log base 10 if you prefer that instead. So take natural log of both sides, because after all, if 2 to the x is equal to 3/5, if this equation is true, then if I take log of both sides, the equation will still be true. And the equation will still have the same answer, the same solution. And then, of course, you have natural log of 2 to the x power. That x will come down as a multiplier, just like last time. And then you can divide both sides by that natural log of 2. So go ahead and evaluate this on your graphing calculator and see what you get. Make sure that you get this answer, this negative 0.737. So I'm going to pause for a couple seconds to have you put this in there. Make sure that you use parentheses carefully, appropriately, to take that logarithm of 3/5. So we have natural log, of 3/5, close parentheses, divided by natural log of 2. Okay. Any questions on this problem? Now, how could we check this answer? Yeah, plug it back in for x. So I'm going to go back to my graphing calculator, and I'm going to take 5 times 2 raised to that answer. So here we go. So I'm going to do 5 times 2 raised to that answer. And indeed, we got 3. So that really was the solution. Everybody see what I did there? Anybody want me to repeat it? Okay. All right, and if I am going too fast, please let me know and I'll back up or slow down or whatever. I'll adjust as necessary. All right, here's the next problem. I'm going to again give you a couple of minutes to see if you could solve this. So I'm going to pause my recording. Okay, so let's go ahead and start looking at how to solve this. And I had already mentioned earlier that it might be a good idea to take a logarithm of both sides. So, for example, a natural logarithm. Again, the base doesn't really matter, but at the end of the day, you want to have a base that you can actually solve with your calculator. So natural log is a good choice. And then those exponents will come down for each of those logarithms. That exponent of x minus 1, for example, for the left-hand side will come down as a multiplier of x minus 1. And that exponent of 2x plus 3 will come down as a multiplier. Now, treat natural log 2 as just a number. And treat natural log 5 as just a number. So when you go about now solving this equation algebraically for x, remember that natural log 2 is just a number, natural log 5 is just a number. What I typically advise my students, if you don't like natural log 2, just temporarily replace it by some symbol, like a happy face or something, right? Or temporarily replace natural log 5 by a moon or something, I don't know. By some symbol that you can temporarily put in there until you actually solve for x, and then substitute those respective natural logarithms back in. However you want to do it, but I'm not going to do that though. Now we go ahead. Now, on the left-hand side and the right-hand side, we'll multiply those out using the distributive property. Okay. On the left-hand side, we have natural log of 2 times x and natural log of 2 times negative 1. On the right-hand side, 2x times natural log of 5 and plus 3 times natural log of 5. Again, what we're after is to solve for x. So you identify those expressions that have x in them. And you want to move those expressions over to one side of the equation and everything else over to the other side. So we're going to probably subtract 2x natural log of 5 over to the left-hand side, or x natural log of 2 to the right-hand side, and then move the other stuff over to the opposite side. So as it turns out, they're putting the x expressions on the left-hand side and then the numerical expressions to the other side. Everybody see what we did there? All we did was we subtracted 2x natural log of 5 from both sides. See this one right here? We just subtracted it from both sides so that it effectively moved it over to the left-hand side by subtraction. And we also added natural log of 2 to both sides. So you see it over here. Okay? Want me to back up? Yeah, I'm going to back up just one moment. I'm just going to erase this ink. Are we good at this step right here? Okay. And then remember, you want to get your x terms together on the same side of the equation. So that's why we're going to, we typically choose the left-hand side as the side that contains our variable expressions. So that's why we subtract the 2x natural log of 5 to get it moved over to the left-hand side. And then same business for the natural log of 2. We'll move it over to the right-hand side by addition. Okay? Okay? And both of these expressions on the left have x as a factor. So we can go ahead and do the opposite of the distributive property, which basically, and normally the forward part of the distributive property says that, A times B plus C is AB plus AC, right? Well, here we're going to do the opposite. We're going to factor out the x from the two expressions on the left-hand side. And now you have natural log of 2 minus 2 natural log of 5, which is just a number. On the right-hand side, you got 3 natural log of 5 plus natural log of 2, which is just a number. And then divide both sides by this number, by this natural log of 2 minus 2 natural log of 5, so you could isolate x. Uh-oh. So we're going to restart my program. Sorry about that. So divide both sides by that stuff in the parentheses, and then plug that whole thing into our graphing calculator. Hold on, let me pull up my presentation here. For some reason it crashed on me. Luckily I wasn't recording the ink annotations. Oh, there we go. So we're down here. Oh, that's interesting. Crashed on me again. I'm going to have just to move beyond that slide. I'll have to troubleshoot that later. So anyway, this is what you should have for your answer. But you got to put this whole thing in your graphing calculator. This whole thing right here. So 3 natural log of 5 plus natural log of 2 in the numerator. So 3 natural log 5 plus natural log of 2. So do that in parentheses. 3 natural log of 5, close parentheses, plus natural log 2, close parentheses. Divide that by open parentheses. And then we're going to divide that by natural log of 2 minus 2 natural log of 5. Huh? Yeah. Yeah, I'm just inputting that expression into the graphing calculator. So you could see the keystrokes. Minus 2 natural log of 5. And then make sure that you enclose the numerator within a pair of parentheses and the denominator in a pair of parentheses. The biggest reason why people get this calculation wrong is that they don't observe the parentheses properly. So if we did this right, here's your answer, at least the approximation of it. Is that the same thing that we have down here? Yes, it is. Okay. Any questions about the calculator piece? Okay. I'm not going to go full screen with this again because my computer seems to be crashing. Yes?
So I have a question.
Yeah.
Is the bottom part of your answer the smallest form of the answer before you put it in the calculator possible?
Can you ask that again?
Say if I wasn't going to plug that into my calculator.
Okay.
Would that x equals 3 natural log 5 plus natural log 2 all over natural log 2 minus 2 natural log 5? That's the smallest possible form.
That is the exact answer. And that's about as well, I'm sure there's a way that you can simplify it more, because the fact that you could write 3 natural log of 5 as natural log of 5/3, right? Or 5 to the third power. And then you can multiply that by 2. So you could have natural log of 2 times 5 to the third power. So that would be, 5 cubed is...
Natural log 250.
So 250, right. So, and the divided by natural log of, 2 natural log of 5, that would be natural log of 5 squared, that's 25. And natural log of 2 minus natural log of 25, that would be natural log of 2 over 25. So you could write that as natural log of 250 divided by natural log of, 2 over 25. So you could simplify it that way. It's equivalent. I don't know that it's all that much simpler, though, than what you have right here. It's just a big, clumsy exact number, though. And like I said, for those of you going on to calculus someday, you have to get used to the fact that your answers are not always going to be nice, easy integers or fractions. Sometimes there's big, ugly, exact expressions involving radicals and logarithms or exponentials and stuff like that. Okay. Can I move on, or any questions about this? Okay. By the way, later on, after we're done tonight, would you like for me to email you the link that for the YouTube after I post this? Okay. Oh well. I'm actually making 2 separate videos, one for each of the 2 sections that we're covering tonight. So. All right. So here's our next problem here. 9 to the x power minus 3 to the x power minus 6 is equal to 0. So what is the value of x, which would make this equation a true statement? Now, it might not appear like this, but it's actually a quadratic equation. So you're probably wondering, how in the world could this possibly be a quadratic equation? Well, it's quadratic in form. Think about that 9. That 9 to the x power. Think about 9 as 3 squared. So you have 3 squared raised to the x power. So for this problem, we have 9 to the x power minus 3x minus 6 equals 0. That's a quadratic equation. Write that 9 as 3 squared. So you'll have 3 raised to the 2x power, actually. Okay? Because, you could write 9 as 3 squared. That's going to be 3 to the 2x power, which could be thought of as 3 to the x power squared. So if you are able to see this equivalency right there, then you'll notice, this is just a quadratic equation. Does everybody understand this equivalency right here? Okay, so you know that 9 is 3 squared, right? So that means that 9 to the x power is equal to 3 squared raised to the x power, right? But a property of logarithm says that this is going to be the same as 3 to the 2x. Okay? But then you can say, well, that's the same thing as 3 to the x power squared. That is a property of exponential expressions. Okay? So that is why we're going to rewrite 9 to the x power as 3 to the x squared. Okay? I'm going to erase this ink here. So just rewrite our equation. So now it's kind of in this quadratic form. Maybe you can do a substitution where u is equal to the 3 to the x power. Which means that u squared is the same thing as 9 to the x power. So we could treat 3 to the x as a variable, call it u. And once we solve for u, then we can solve for x. Okay? Now, that being a quadratic equation, at this point in the game, we know how to solve it. We could factor that left-hand side, right, as u minus 3 times u plus 2 equals 0. And by the zero factor property, that means that either u is equal to 3 or that u is equal to negative 2. But remember what u is. And again, you don't have to do the substitution. Some people are perfectly happy just trucking along and just saying this is 3 to the x squared minus 3 to the x minus 6 equals 0. And don't bother with substitution. But I happen to think that substitution is a little easier. So anyway, u is equal to 3 or u is equal to negative 2, but u is equal to 3 to the x power. So that means that either 3 to the x power is equal to 3 or 3 to the x power is equal to negative 2. Now, if 3 raised to the x power is equal to 3, what does that make x? 1. I agree. It's 1. Yeah. Okay, so we... Now look over here, though. If 3 to the x power is equal to negative 2, what does that make x? Doesn't make x anything, because there's no value of x which will make that equation true statement. Because you can't have a positive number raised to any power and the result being a negative number. So we can cross this possible answer out. So we only have one solution, and that's x equals 1. And indeed, if you were to plug in 1 for x into the equation, you have 9 to the 1 power, which is 9, minus 3 to the 1 power, which is 3. 9 minus 3 is 6. 6 minus 6 really is equal to 0. Okay. All right. Any questions so far about solving logarithmic or exponential equations? I don't like red ink. I'm going to go back to my dark blue. Now, real quick, solving logarithmic and exponential equations using your graphing utility. If you have a graphing calculator with you, let's see a problem in which we could use a graphing utility to solve it. Now, why would we want to do that? Well, not all equations involving logarithms or exponentials could be solved using these algebraic techniques that I've been showing you. In which case, we may have to get an approximate answer using a graphing utility. So let's just look at this as an example here. We have x plus e to the x is equal to 2. What is the value of x, or what are the values of x, because there could be more than one solution, which would solve this equation? Now, I'll show you the official answer. Now, what we could do is in our graphing calculator in the equation editor, you plug in x plus e to the x as one function, and 2 for a second function. You graph them, and you look to see where the two graphs intersect each other. So I'm going to go to my graphing calculator and see what that looks like here. Okay, so there's my equation editor. I'm going to put in x plus e to the x as one function. And then I'm going to plug in 2 for my second function. Now, I'm going to let x go from, I don't know, maybe negative 10 to positive 10 in the viewing window, with tick marks maybe every 2 units. And we know that the intersection is going to happen at y equals 2. So I'm just going to let the y minimum be 0 and the y maximum be 4. Maybe I could have the tick marks go every half a unit, 0.5. And then I'm going to go ahead and hit graph. So there's that first function, x plus e to the x, and then the horizontal function was 2, the function y equals 2. And notice that they intersect right there. Now let's zoom in to that a little bit. I'm going to actually set the window. We see that intersection is happening at just a little bit past x equals 0. So I'm going to go back to my window, let x start off at 0, maybe let it go out to 2, and maybe let the tick marks be every 0.2 or so. And then what we want to do is find the x-coordinate of this intersection of those two graphs. We know the y-coordinate is 2, but we want to find the x-coordinate. And what we could do to find that intersection point is, you see along the top row of buttons up here, you see this button right here? You see the letter CALC. It's for calculate. It's for calculating, but you have to hit the second button to get into it. So hit second and hit that button. And go down to option 5. And now they're going to ask us which two curves do you want to find the intersection for. Well, for this problem, we only have 2 curves. But this is a useful thing if we have 3 or more curves, because it's only going to find the intersection of 2 curves. So we'll just go ahead and select that one and that one. Just hit enter both times. And then the guess is going to be close to 1. So you could maybe hit the left arrow button to get close. Move your cursor closer, as close as you can get it. And hit enter. And notice that the x coordinate there is 0.44285544 approximately. All right. Are we all together on this one? Anybody having any issues right now? All right. So we could write this as our approximate x value for the solution. Okay. So there's a little screenshot of that same thing that we just did. So the answer is approximately 0.443 when I round it to 3 decimal places. Or 2 decimal places, 0.44. Okay. All right. Any questions about what we've talked about from this section, section 6.6? Okay. Well, let's take a 10-minute break, okay? So give me a chance to transition from this section to the next section, okay? And let's come back in about 10 minutes and we'll move on into section 6.7.